Hello friends, today we will see about convolutional autoencoders. So this is a very crucial lesson because the concept of autoencoders is very widely used and quite popular in with images where we try to extract the essence out of the image and also get rid of the redundant noise. So it's very popular to work with convolutional neural network in autoencoders. So just to recap, we are working with MNIST handwritten dataset, and we will be defining an encoder and decoder, which are the two components in an autoencoder, and then we will generate a new image. And the main thing is that this middle layer has the least number of nodes in it. So in essence, we are representing this whole input data into a very few nodes or in a compressed form. So earlier we had defined just simple neural networks with some nodes. So in this case, we will apply it to convolutional setting. So the first layer will be input layer of size 28 cross 28 cross 1 because our MNIST handwritten data sets are of 28 cross 28 grayscale images. So this is our input layer. And then we will add a convolutional layer. And we will add 16 channels to it. And we will keep the padding same, and we can use some 3 cross 3 filter. So if we are doing the same padding, then we again have 28 cross 28, but the number of channels will be 16. So this is our next layer. So we can say it conv1, and then we can apply a pooling on top of it, because first we will be shrinking it in the encoder part, and then we will decode it. So right now we are constructing the encoder part. So this is 28 cross 28 cross 16. Then we apply pooling 2 cross 2, stride 2 and step size 2. So it will shrink to 14. So now we have 14 cross 14, and number of channels is same, 16. And we will be applying max pooling. And now we have 14 cross 14 cross 16. So we have came from 28 cross 28 to 14 cross 14. Then we will apply further convolution on top of it, and with 8 filters. So we can shrink it to 14 cross 14 cross 8. And then we will apply pooling, again same 2 cross 2, max pooling. And our it will reduce to 7 cross 7. So this is not drawn to scale, it should be much smaller. So we have this 7 cross 7 cross 8 volume. And then we can apply further max pooling and shrink it further to 4 cross 4 cross 8. And now we can add a conv layer on top of it with same padding. So we will be again left with 4 cross 4 cross 8. And now we will treat this as our encoder. This is our compressed representation, or we also call it bottleneck layer, because this is the smallest dimension in our network. So now we are done with the encoding part. Then we can upscale it and try to decode whatever is captured in this. This image was input here, and we shrink it to this layer, and the output will be same as image for reducing the loss function. And with enough training, the network will learn to represent this image in this many dimensions. So now we will add the decoding part. So by up, I mean upsampling. So we have upsampling layer in Keras, and we will shortly see it in the implementation. And with upsampling, we will scale it to this representation. So while applying max pooling, it will be reduced to 7 plus 1 by 2. If it would have been 8 cross 8 cross 8, then also it would have come to 4 cross 4 cross 8. But so now it's 8 cross 8 cross 8. So we have done upsampling here. Then we will do convolution, and it will come back to 8 cross 8 cross 8. And then we can apply further upsampling and make it 16 cross 16 cross 8. Now you are seeing that when we are doubling, it will ultimately come to 32 cross 32. But here we had started with 28 cross 28. So the trick is that we were doing same convolution here. So we were adding some padding so that size remains same after convolution. But here we will apply valid convolution where we will not pad zeros. So now we have 16 cross 16 cross 8, 8. And then we can apply a convolution here. 3 cross 3, and we will not pad anything. That is valid convolution. Then it will shrink to 14 cross 8. Because if you have 16, height is 16 or width is 16, and we do convolution, then we will overlap this 3 cross 3 on top of it. So this will generate 1 pixel. Then we will move it here, this filter, and we will generate next one. So we see that when we have covered 3 cells, we have generated 1 input. When we reached here, 4th one, then we have 2 pixels. And when we reach till 16th, we will have generated 14 of these pixels values. And we have reached till end, so we will not slide this window further. Similarly in the vertical case, so this 16 cross 16 cross 8 will reduce to 14 cross 14 cross 8 if we do not apply any padding. So we will not write same here. Same means we pad so that input shape is same as output shape. So now we have come to this 14 cross 14 cross 8, which is similar to this. And now we can do further upsampling and reach 28 cross 28 cross 8, and then we can apply more convolution layer with 1 filter so that we reach back to this 28 cross 28 cross 1. So it will be more clear. I think there is too much in this slide, so it will be more clear when we implement these layers ourselves. So the first part is same as our previous videos. We will be importing some libraries, and in particular you see one additional entry here, upsampling, because we will be using upsampling layer of Keras. And then in some of the videos you may have seen sequential APIs being used, where if you have all the layers of the network are stacked one after other, then you can use sequential APIs of Keras. But it has limitation, although it's very simple. You just need to keep on adding layers, create a model, and then model.add layer. But when you have complex structure, like when 2 inputs are coming to a node, or one node is giving 2 outputs, which a network is diverting from there. So you need more finer control, and then you need the functional APIs of Keras. So I will be using functional API in this case, although not required for our case. So that's why this input layer is here, and I have not imported sequential APIs. So now once we have imported the libraries, let's load the dataset. And we are again working with MNIST handwritten dataset. And the main part of this lecture is this defining the convolutional autoencoder layer. So first we will define the input layer, which was 28 cross 28 cross 1. And we can also additionally give names to our layers. So if we don't give name, Keras will automatically give some dummy name like input 1, input 2. But let's explicitly give some name to our layers. So this is the input layer. Then we will, you can see here we had added one convolutional layer with 16 filters. So let's exactly do the same thing in this code here. So we will use this convolution 2D. And we will have 16 filters here. 3 cross 3 filters we have been using, and we keep padding equal to same. So it will pad appropriate number of zeros so that output is same as input. And activation is relu. And we will again give a name to our layer. Let's keep it con1. And then it will take as input the input layer, the previous layer. And then we will do max pooling. So here after convolution we did max pooling to shrink it to 14 cross 16. So now we will add a few more of these convolution and pooling. So in the next level we will have 8 filters. Kernel size would be same, padding would be same, activation relu, and name conv2, and it will be applied on X layer. And then similarly for pooling, and then a few more of these. So this time again 8 and 3. So now we have defined the encoder part, and now we will apply the decoding part. So our encoder is defined. Now we will use the upsampling. So in pooling we were shrinking the size, in upsampling we will double the size. So in the last case, we did not apply same convolution because it would double to 32 cross 32 in this case. So we will skip same in the last one. And then finally we need an output layer. And let's give a name to it. So now we have defined our layer, and we will define the model. And in our case, for this convolutional autoencoder model, inputs is this input layer, and outputs is this output layer. And we can give a name to it. We can call it CAE for convolutional autoencoder. And then we are ready to compile the model, where we will need to specify the optimizers and the loss function. You can try with different optimizers and loss functions, or you can even define your own loss function. Let's also print the summary of model so we can see which layers are having what dimension. And now let's run it. So in the output layer, we have done some mistakes. So now our model has compiled successfully, and with this model.summary, you can print the structure of the model. So this is the input layer, 28 cross 28 cross 1, and this none stands for batch size. When we will, it's not known at the moment. When we fit the actual data on it, and there we specify the batch size. So this dimension will represent the batch size, none. So this is 28 cross 28 cross 1, then 28 cross 28 cross 16, and these names are coming from whatever names we had given. And then shrink to 14, 7, then 4, and this is our bottleneck layer or the compressed representation. And then we start decoding it. So double it, 8, then 16, then we apply valid convolution to make it 14, then double it, upsample to 28 cross 28 cross 8, and finally 28 cross 28 cross 1, which is same as our input dimension. So now we will fit the data. So we have already loaded the MNIST dataset, And in the case of autoencoders, y is same as x, so we pass x train twice. And here we specify the batch size. So batch size denotes after how many passes through the different data, it will update the weights. So even if we don't pass the batch size, the default is 32. So you can skip that. And we will run it for 50 epochs. So let's run it. So it will take some time. I will get back when it completes 50 epochs. So now it's in the last epoch. And it has now completed training. So we will do prediction on some new data. And we will store it in out images. So we are done with the prediction, and now we will just plot the data to see how correctly it has generated. So you can see this is the generated image, and you see it's pretty close to the original one. So the autoencoder was able to learn a compressed representation of data in its bottleneck layer. So this was a very crucial lesson, and hope you understand it completely, because it will be helpful in studying further the variational autoencoders and other high-end variants of autoencoders. Thank you.